Hui-shi1, come from King University, Professor Hui-shi1's lab. It's my great pleasure to make a presentation here. The title of my presentation today is Construction of Chiral Selector modified surface for chiral recognition of mandelic acid by quartz crystal microbalance. At the beginning, I would like to mention about the background of this research. As we all know, chirality is one of the basic phenomena of nature in the life. Chiral initials are still isomers that are mirror images of each other, just as one's left and right hand are the same but opposite. Initials often show very different behaviors. For example, our thalidomide is a drug for sleeping. However, as the initial of it is teratogenic. Therefore, chiral initials plays very important roles in pharmaceutical and biotechnology field. There are two basic ways to obtain chiral initials: resolution and asymmetric thesis. Resolution involves kinetic resolution, stereomeric crystallization, and professional crystallization. The stereomeric crystallization has the advantages of high yield, high optical purity, and relative simplicity. The principle of the stereomeric crystallization is based on the formation of the stereomeric sort of two initials and then separate them by conventional separation method. The key step of this method is the choice of resolving agent. However, up to now, this step is still trial and error. So we want to use other methods to screen this resolving agent, and we believe that the chiral recognition results can provide useful information for for the selection of resolving agents. QSEM is a newly developed chiral recognition method. The QSEM detection device is composed by a QSEM sensor, an oscillator, and a frequency counter. The QSEM sensor is composed of an 80-cut quartz crystal and two thin layers of gold or platinum coated on it. When materials is loaded on the QSEM sensor surface, the oscillation frequency of it will decrease. This frequency decrease is related to the mass loaded on the sensor surface through this solver equation. QSEM is well known for its high sensitivity and low cost, and it has been widely used in the analytical chemistry field. So the aim of this work is to use QSEM to study the chiral recognizability of mandelic acid on chiral selectors. Here we use alpha-adenine and acetylene modified surface. To fulfill this purpose, we use a VDMA reaction technique. This shows a VDMA reaction device. This is the Chiral Selector modified sensor. It was placed in a reaction chamber, which was located in a constant temperature oven. And this represents the reaction solution, such as in our experiment is L-mandelic acid solution or D-mandelic acid solution. And here shows the reaction process of this method. A is the Chiral Selector modified surface. B and C represents the solute molecules, L-mandelic acid and D-mandelic acid diffusion and recognition reaction on the sensor surface. And D is the final assembled surface. Before the VDMA reaction, we detect the frequency F1. And after the VDMA reaction, we detect the frequency again, F2. The difference between these two frequencies, delta F, reflects the materials attached to the sensor surface during the VDMA reaction period. In this work, we select two molecules to construct the chiral surface. Here shows the construction of alpha-phenylalanine modified surface. It was composed by two steps. First, a monolayer of ATP, 4-aminosulfone. We say ATP was immobilized on the gold surface of the sensor, and then alpha-phenylalanine was immobilized by using diazo coupling reaction. And here is the construction of L-cysteine modified surface. Because L-cysteine has the cell group, so it can be immobilized on the gold sensor surface directly through the gold cell bonding. The modification of the QSM sensor surface was characterized by several methods. This is the QSM frequency detection results. From here we can see the frequency decrease and the mass increase after each modification step. This reflects that the ATP and the alpha-phenylalanine modified on the sensor surface. After ATP modification, the frequency decrease is 32.3 Hz, corresponding to 33.9 nanogram of ATP coated on the sensor surface. Translate to a surface coverage is 0.68 nanomole per square centimeter. And this is the contact angle results. For the bare gold surface, the contact angle is about 88 degrees. After ATP and alpha-phenylalanine modification, the contact angle decreased, showing that the hydrophilicity increased on the sensor surface. This is reasonable because the amino group and the carboxyl group has the hydrophilic property. As for the L-cysteine modification, after L-cysteine modified, the contact angle decreased to about 55, also showing that the increase of the hydrophilicity on the sensor surface due to the hydrophilicity of amino group and the carboxyl group of L-cysteine. And this is the electrochemical reduction desorption results. For the first scan, we can see a cathodic peak at about minus 0.54 voltage. This is due to the reduction desorption of ATP from the gold surface. During the successive second scan, we can see that this peak almost totally disappeared, meaning that most of the ATP on the gold sensor surface was dissolved from the sensor surface during the first scan. So, according to the electrochemical principle, we can calculate a surface coverage of about 0.73 nanomole per square centimeter. And this result is similar to the results obtained by QSM detection method. And we also use CV to characterize the sensor surface. This is the CV results obtained in ferrocyanide solution. For the bare gold surface, a pair of good-shaped peaks was appeared. This is the normal case. After ATP modification, these two peaks increased. The peak height increased, and the peak distance between these two peaks decreased a little. This is due to the amino group carried a positive charge in the solution, so it will attract the negative ferrocyanide ions to the electrode to make the electrochemical reaction. After alpha-anion modification, both of these two peaks totally disappear, meaning that the electron transfer on the electron surface was totally blocked. And we'll also use XPS to characterize the surface. This is the XPS result of alpha-anion modified surface. A represents the ATP modified surface. B represents the alpha-anion modified surface. From the S2P region, we can see that on both of these two surfaces, they have the sulfur atom peaks. So it's related to this sulfur combined to the both surfaces. And for the nitrogen 1s region, for ATP coated surface, only one peak was obtained due to the nitrogen atom in this amino group. And after the alpha-anion modification, two new peaks appeared. Is related to this diazo linker. And as for the oxygen 1s region, for ATP modified surface, no peaks was obtained. After alpha-anion modified, two peaks, new peaks appeared related to this carboxyl group. And this is the XPS results of alpha-spin modified surface. All of the S2P, N1s, and O1s region showed clearly sulfur, nitrogen, and oxygen atoms on the sensor surface. This is due to these atoms in this alpha-spin modified surface. So, all of these QCN, contact angle, electrochemical reduction, and CV and XPS results show that the modification on the surface is successful. So we use this Chiral Selector modified surface to check the recognizability. So the Chiral recognizability on this selector modified surface was checked by sensing L and D mandelic acid by using VDMA reaction method. Here we can see that this is the results obtained on the alpha-anion modified sensor. For pure water, do not have any frequency change. For D-mandelic acid, the frequency only decreased a little during the first 2 days, and after that, it remains almost stable. Meaning that only a few amount of D-mandelic acid was attached on the sensor surface. For L-mandelic acid, the frequency decreased almost linearly during the beginning of the VDMA reaction period, meaning that the longer the reaction time, the more L-mandelic acid attached to the sensor surface. After that, this frequency change tends to level off, meaning that the reaction equilibrium was reached. So from these results, we can see that this alpha-anion modified sensor surface has the recognizability on L and D mandelic acid. The Chiral discrimination factor obtained here is about 7. We also detect the contact angle after the VDMA reaction. For water and the D mandelic acid do not have distinct changes on the surface. However, for L-mandelic acid, after the VDMA reaction, the contact angle decreased about 60 degrees, meaning that the hydrophilicity increased on the sensor surface. This is due to the L-mandelic acid aggregate on the sensor surface, so increase the hydrophilicity on the surface. And this is the Chiral recognition results obtained on the alpha-spin modified surface. The frequency change tendency is similar to that obtained on the alpha-ionic modified surface. For pure water, no frequency change was obtained. For D-mandelic acid, the frequency only decreased a little during the beginning of the VDML reaction period. For mandelic acid, also the frequency decreased continuously at the beginning of the reaction, VDML reaction period, and after that it remains almost stable. So the conclusion is similar to that obtained on the alpha-ionic modified center surface. And the carrier discrimination factor obtained here is about 5. So compare these two results obtained on the L16 modified surface and the alpha-ionic modified surface, we can find two differences. The first one is the frequency change rate is different. For the frequency change rate for mandelic acid on the L16 modified surface is much slower than that obtained on the alpha-ionic modified surface. This means that the carrier recognition reaction rate on the L16 modified surface is lower than that on the alpha-ionic modified surface. And for the second difference is that the carrier discrimination factor is different. For the factor obtained on the L16 modified sensor is lower than that obtained on the alpha-ionic modified sensor. This means that the L16 alpha-ionic modified surface was more preferred to combine with mandelic acid than D-mandelic acid, than L16 combined with mandelic acid and D-mandelic acid. So it means that alpha-ionic was higher selectivity than L16. So in conclusion, in this work, we used two carrier recognition surfaces were built by using alpha-ionic and L16 as the selector. The second one is the carrier recognition of L and D mandelic acid on these two carrier surfaces were successful by using VDML method. This result suggesting that both alpha-ionic and L16 can be the resolving agent for separation of chiral mandelic acid. However, when we compare the chiral recognition results obtained on L16 and alpha-ionic modified surface, we'll find some differences, so we can make the conclusion that alpha-ionic may be a better resolving agent than L16 to resolving chiral mandelic acid. Actually, in our lab, we use diastereomeric crystallization method to separation L and D mandelic acid using alpha-ionic or L16 as the resolving agent. We also obtained similar results. At last, thank you very much for your